In this lecture, I'd like to tell you a little bit about how the framework of acyclic partial matchings and Morse complexes can be used to simplify our lives when we are trying to compute persistent homology. As with all things persistent homology, the starting point is a filtration. So let F be a, let's say, R plus indexed filtration of a simplicial complex K. And now we know how to compute the persistent homology groups, but we're going to do it in a much quicker and more efficient fashion, the way we did with ordinary homology groups in the last few lectures. Now, the goal is to construct a Morse filtration. With the same persistent homology. So that's the goal, and we're going to do it by first looking at the data of a filtration in the form of a function. So remember that there exists a function, a monotone function, which I'll call B from K, which assigns just positive real numbers to simplices of K, that encodes F, right? So it tells you when every simplex is born, and this function sends sigma to the number B sigma, which is the infimum over all non-negative T, such that the simplex sigma is in the subcomplex FTK. So that's the associated monotone function. And so let me, the basic idea fits into one picture. So I want to show you the picture before we do any algebra. So consider this filtration. So it's the total simplicial complex is just this one interval, and I'm going to write the B values of everything. So this is born at 0. This is born at 0, this is born at 1, and then no other simplex shows up. So that's the full simplicial complex. And if you looked at its 0th barcode, you would get two connected components born at time 0. Here's time 1, and what would happen is that one of these connected components lives on forever, and the other one, of course, meets its demise at stage 1 of the filtration. The reason it does that is that the minute that edge comes in, we lose one dimension in the Betty numbers. Now, what I want to point out is that you cannot just impose an acyclic partial matching, ignoring the births. So if this, for the same complex, this is birth 0, 1, 0, if you try to make that partial pairing sigma, that sends the vertex on the right and pairs it with the edge, then the Morse complex just contains the critical bit, which is that vertex 0, and the bar for that, of course, looks like this. So these two barcodes, because of the short bar, are not going to be equal. So it's not enough to just take any old partial matching and forget about the structure of the filtration and expect somehow that the persistent homology will be preserved. The good news is that this type of mistake, where you paired things born at different times, is the only mistake you can make. If you don't make this mistake, the theory of acyclic partial matchings and Morse complexes just flows into the persistent framework. So let's make this the class of matchings that are good precise. So an acyclic partial matching sigma on K is compatible with the filtration we have. So I'll just call it F compatible. So that's the term we're defining here. So maybe give it a different color. So is it F compatible if whenever you have a pair, sigma tau, in this matching, the births are equal. So we have B sigma equals B of tau. And this very simple condition, that these two simplices that you pair, any pair of simplices must have the same birth if they're in sigma, this is all you need. So this will make everything nice and easy for us. So let me begin by saying what the point is. So here's an extremely straightforward result. I mean, I'm not sure it deserves to be called a proposition, but we'll call it that anyway. So if sigma is an F-compatible acyclic partial matching on K, then for any sigma path, let's say rho, so remember these look like paired sigma 1 less than tau 1, and then some arbitrary sigma 2 less than tau 2 all the way, m. Okay. Then anytime you have a sigma path, the B values decrease from left to right. So another way of saying this is, I guess B of sigma I is bigger than or equal to B of sigma j for all I bigger than j. And remember, because these backward pointing things always are elements of sigma, it's enough to tell you what happens to the sigma births, because the birth of the tau I is going to be the same as the birth of the corresponding sigma by compatibility. And the proof is I mean, it's silly, right? It's just so you take this path, rho, and let's just copy it down. So here it is, and here I'm going to write some B's, right? So this is some number for sigma 1. This is some number for tau 1, sigma 2, tau 2, sigma m, tau m. And by compatibility of sigma, we know that these numbers are equal. But we also have an additional piece of information, which is that we have greater than or equal to's relating each tau I to the next sigma I plus 1. So the equal signs happen because of compatibility, and the bigger than equal to signs happen because B is monotone. And so faces have to be born before the larger simplices. And that's the proof. I mean, if you look at the numbers from left to right, they're decreasing. I mean, I'm not saying they're strictly decreasing. They could all be equal, but you certainly cannot have a simplex that shows up later on in the gradient path that is born after one of the simplices in the beginning of the gradient path. So there is a sort of monotonicity even to these paths. They go from things born late to things born early. Okay, once you have this, it's a fairly straightforward corollary that the Morse complexes are well behaved. So here's some notation basically. This is to avoid me writing superscripts of subscripts. So let's see what the notation is. So note that for all t bigger than 0, we have a subcomplex ftk of k, right? That's by the definition of a filtration. And sigma restricts to an acyclic partial matching on ftk, which I guess we will call this restriction sigma t. So these are sigma t consists of all the pairs in sigma of simplices whose birth times, and remember both paired elements have to have the same birth time by compatibility. These are all the simplices of birth time t or below. So that's and if one of those, if that partial matching was cyclic, then all of sigma would be cyclic. So we don't have to worry. It's going to be an acyclic partial matching when you restrict to the subcomplex. So the corresponding Morse complex, if you think about what we'd want to call it, is the chain complex. It will be C of sigma T. So that's the partial matching. This is the subcomplex, and then I'd have to write some K's, and then the boundary operator would be D sigma T, right? I do not ever want to write this again, so I'm just going to define this as MT dt. So this is defining the stuff on the right to mean all that junk on the left, just so I don't have to write it again in this gory superscripts and subscripts. Okay, so with that notation in place, here's another proposition. For every t less than equal to s in R plus, we have an inclusion of Morse complexes. So the tth Morse complex includes into the sth Morse complex, ds. Okay, so let's try and see why this must be the case. So this is a chain map, so it's an inclusion of chain complexes. That's what we'd like to show. So on the level of the chain groups, there's no doubt, right? So MT is generated. This is the vector space generated by critical simplices with b values less than or equal to t. So this includes into MS, because if you have critical simplices born before S and S is bigger than T, then then all the simplices that were born at T or below are already included. So the vector spaces include. So we need to check that this square commute. So MTK, so these are this is the vector space generated by k-dimensional critical simplices in the subcomplex FTK of the filtration. And this includes into MSK as already discussed. But now there's a boundary operator that connects you to the k-1 simplices. And here, similarly, boundary operator. We want to show that this commutes. Which is to say, if you had a simplex that generated MTK, that simplex would still be present in MSK, and we want to show that its boundary here, dt alpha, is the same as ds alpha. And if you remember, the formula for the Morse boundary operator was a sum over gradient paths, right? So there was a sum over gradient paths term. So if you have any sigma path, and I'm not restricting to sigma t or sigma s, just the big partial matching sigma. If you had any sigma path connecting to alpha, so this alpha is going to be a critical k-simplex in MT, or I guess I could just say in FTK. So in that subcomplex. So if you had any such path, it would start alpha bigger than sigma 1, less than tau 1, bigger than, right? So this would be the sigma path going somewhere. So any time you have something like this, we get sigma 1 is a codimension 1 face of alpha, which means it's at least a face. So B of sigma 1 is less than or equal to B of alpha by monotonicity. But this is alpha was already present in FTK, so that means that the birth of alpha is less than or equal to T. So what this is saying is that the first bit of any gradient path that connects onto alpha is going to have a cell or simplex here that's already present in FTK. And by the monotonicity of these paths, which we established with our silly calculation up here, the entire path must consist only of simplices that are present, that were born at t or before. So let's write that. So every simplex appearing in this path is present in FTK, which means as you add more simplices going from the T subcomplex to the S subcomplex, the gradient paths that you're summing over never change. So this forces ds of alpha to be equal to dt of alpha for all s bigger than t. And that proves that this diagram upstairs commutes. This is what we wanted to show. And again, scary commuting diagram maybe, but this is all a simple consequence of the fact that the paths are well behaved with respect to this birth function of the filtration. Okay, so now we have, what is the upshot? Is that we have a filtered chain complex. Which is mt dt for all t bigger than 0. So these are all nested sitting inside each other. And so for all k bigger than equal to 0, the homology hk of mt dt is a persistence module. So it's a one-parameter family of vector spaces. So that's great. So this is for all t bigger than 0. And now when you have this persistence module, you want to compare it. You want to compare it to the original persistence module, which would be hk of ftk. Right, this for all t bigger than 0. So that's what we want to compare. I mean, we've whittled down this giant filtered complex into a filtered Morse chain complex, which is called MT-DT here in the shorthand notation, and we want to compare the two persistence modules. And here's the main theorem. This is the main result for how acyclic partial matchings make computing persistence easier. The main result is that the barcodes of HK, FTK, this persistence module are exactly the same as the barcodes of the Morse filtered chain complex. So HK, MT, D, this is again for t bigger than 0. Okay, so this is what we'd like to prove. And in fact, a stronger, you can say nicer, stronger algebraic statements, which is that that in fact these on the level of persistence modules already you can relate these two, the big one and the Morse reduced one. And so here is the proof. So for every t less than equal to s in R plus, we have diagrams, and I'll just make one big diagram, but we have one for every pair t less than equal to s. So of the following type. So you're going to get the kth chain group of FTK, including into the kth chain group of FSK. And similarly downstairs, you're going to have the Morse complex inclusions, which we just proved in the previous proposition. Okay, so these are inclusions. And now, if you remember from our previous lecture where we established the Morse equivalence, there's a map psi that takes the big complex upstairs to the small Morse reduced one. And since these are indexed by t, I'll just call this psi tk. And similarly, there's psi s k. So we're reducing those. And of course, there are maps back, and those were called phi in the previous. And what we know about these is that they form a chain equivalence, right? So that weird symbol there is that these two maps are going to give you a chain homotopy equivalence. And now, and of course, these are also all on the level of k-dimensional critical simplices. And now, in fact, if you take this diagram with just the red arrows, and if you take this diagram with just the blue arrows, you can show just by looking at the formulas for psi and phi, which were put up in the next lecture, that in the previous lecture, that it doesn't matter whether you do psi and then include, or if you include and then do psi. The result is going to be the same, and the arguments are very, very similar to the ones we used up here when showing that the boundary operator is also preserved under inclusion. So these commute. So what you have when you pass to homology are the following. So you have HK, FTK with some not necessarily inclusion map into HK, FS. And now you have some map induced on homology. And again, HK psi S. So let me change those phis to psis because that's what they were supposed to be, the red ones. I keep writing phi for reasons unclear to me. Here we go. Psi T, HK psi S. So those are the two downward pointing induced maps on homology. And of course, down here you'd get HK of MT and HK of MS. So these are downward pointing maps. Then you'd get the upward pointing maps. These arise from the maps in homology induced by the phi chain maps. Phi T. And of course, these are mutually inverse. So here when I write equal, I really mean going down and coming up is going to give you the identity. So this is a zero interleaving. Of the two persistence modules. So the barcodes are equal because they have to be distance zero in the bottleneck by the stability theorem. And that's the proof that discrete Morse theory or acyclic partial matchings can be made compatible with the structure of a filtration, so that if you want to compute these barcodes of any filtered chain complex built on a simplicial complex, for instance, you can impose a nice filtered acyclic partial matching that's compatible with the filtration. So it only pairs cells simplices that are born at the same stage in your filtration. And if you do that, then you can run the entire machinery of reducing large complexes to small ones, but you can do it in a filtered way so that the barcodes are all preserved. So hopefully that all made sense. In the next lecture, which is the final one for the course, we're going to similarly adapt this machinery to make our lives easy when we compute sheaf homology. So see you there.